Okay, yeah, welcome back again. Here we have Antonio Cuni, which most of you will know for being one of the main developers behind PyPy. But today he will tell us about, he will teach us about some Python white magic. Okay?
Thank you. So. Thank you and good afternoon, everybody. You are a lot, and now I feel the responsibility. I hope to do a great talk. So, well, just a few words about me. As Luca just said, I'm one of the PyPy core developer. Right now I'm doing porting onto Python 3K. I also own a couple of other pet projects like PDB++ or Fancy Completer. I'm a freelancer consultant and trainer. You can find more about me at my website, but this is not about me, it's about the talk. What will you find in this talk? Well, basically, it's a collection of hacks, which I did during my work on my projects. However, yes, they are hacks, but they are hacks that I did to solve real-life problems. And I think that even if some of these are considered like magic, they help to improve the code you write, and so I just wanted to present this collection of hacks. Of course, you might not like all of them, because they are a bit outside the usual Pythonic style of development, so feel free to tell me that you hate everything I say. But more importantly, I wanted to use this talk as an excuse to teach you and to tell something about the internals or some features that are considered advanced by the Python language or the Python virtual machine. So we will see something like function and code objects, how the bytecode works, meta classes, decorators, import logic if there is time, and yes, all of it is in 35 minutes. We will see if we manage. What is Python? Well, I suppose you already know about it, something. It's a powerful language. It has a surface of simplicity. Everything seems to just work as expected. However, if you look at the internals of the language, you can see that simplicity is like an emergent property of a lot of internal rules. There are a lot of them, special cases, layers and layers, and if you know about them, if you know how things actually work behind the hood, we can use or abuse them to fit our need. Usually these techniques are considered black magic. Why black? Because if you don't use the standard techniques, you make your code harder to read, harder to maintain. Maybe you rely on some implementation details, so your code works only on CPython and not on PyPy or Jython or IronPython, and you change the version of the language and then things breaks. So usually all these things are considered not to do or not very elegant. But what is magic? Well, this is the obligatory citation. Any sufficiently advanced technology is undistinguishable, well, this word I cannot pronounce, from magic. So yes, the point is that you look at these things as magical because you don't know much about it. You just see this code, does strange things, it somehow works, and you take it as granted. But if we go inside and understand what's under the hood, then these things are not magical anymore. They are just normal code you can use to improve the rest. So you don't need to be like this to do magic in Python. It's sufficient to be like a normal programmer which knows about the language and it's happy because it makes better code. That's why I chose to call it white magic, because yes, it's still magical in the sense that it's unusual code, but if it's used in the right places, it can help you to have better code, more maintainable. Of course, there are cons, but there are also some advantages in doing this. But the important thing is that you really understand what's behind it and use it with care. So let's try with the first problem I want to present. It's something that I had to do while developing PDB++. What is it? PDB++ is an extension of the standard PDB module to debug Python programs. I really didn't want to develop a new debugger. The standard PDB one works kind of well. It has some problems. I wanted to solve it, to add new features, like for example coloring or syntax highlighting, etc. And I wanted it to be a drop-in replacement, so I wanted to keep the same API, both at the class level and also at the module level. But then we have a problem, because how do you extend the module? We all know about how to extend a class. We just subclass it, override the methods, and everything works. But PDB is a module, and there are top-level functions. We want to extend them in some way. We will see how. And we don't want to copy and paste. We really want to reuse the existing code in PDB. So this is what I had to do in the first place. On the left, you see the original pdb.py module in the standard library. It has a class named uppercase PDB, which has methods and logic. And then it has some module level function, which are just some nice helper around the class. For example, there is setTrace, which instantiates PDB and calls the method setTrace on it, passing some arguments. And the arguments are computed using some logic, which I want to reuse. I don't want to copy. The same for main. The main does exactly the same. It instantiates a PDB class, then calls a method on it. So what can we do? Well, I write my new PDB class, which subclasses the uppercase PDB class of the standard module, and this is fine. But then how can I extend these two functions? There are more than these two, of course. Well, one possibility is to just try to call the function from the original module. So it is pdb.setTrace that you can see here. It's really calling the setTrace function defined on this module. But what is the problem? Can anybody spot the problem with doing this? Wrong class, exactly. The problem is that if you run this function, then this class is instantiated, and this class is looked on the module namespace, so we instantiate this class, and not this one, which is the extended functionalities. So we could copy and paste the code from the standard PDB module, but of course it's not a real solution. What can we do? Well, there is this magic I can show you directly from the prompt, maybe. So we go from the parental prompt, we write a function with just print the value of a, where a is a global variable. So I call it, well, of course it works. Then I import my magic module. Okay. Sorry for the... Okay, I import my magic module. I use this rebind globals magic function, which takes foo, takes a dictionary, which is our new globals. Now foo2 is another function And now, instead of looking up the name A in the global of foo, you see that foo is still looking 32, we look in our new dictionary, which I define here. So we can simply use these for solving our problem in PDB. So how does it work? Well, foo is an object, is a function, and in Python, you know, everything is an object. It's an object which has some attributes. I show only two of these today. One is func globals, which is a dictionary of containing the global variables, which we will look up, and the other is func code. So func globals, as I said, is a dictionary that contains well, our global scope. Func code is a code object. What is a code object in Python? It's the object which contains the actual logic inside a function. Among the other things, it contains these co-code attributes, which contains the actual bytecode. This is this assembly, and we can see that there is this load global bytecode at the beginning, and we are trying to load global the name A. What it happens is that when we execute the code object, we go to load global the name A inside the func globals dictionary. So what happened when we did the rebind globals is that we created a new function. And we reuse the same code object. You see this red link here. But we use our new func globals dictionary. So when we execute the function foo2, then this load global goes on the red link and finds the other object. So this is the implementation of this magic spell. Well, it's very easy at the end if you think about it. What we do is simply to pass it the function, the global dictionary we want. We can instantiate a function in CPython. It's just another object. We can import the module types and function type, and we pass the code object from the original function, the new globals, the same name, and the same defaults, return it, and it's done. So we can simply solve our original problem by rebinding the globals of set trace and main. Then when we execute them, our new PDB class is found and instantiated. So as I say, there are pros and cons of everything. The advantages of this technique is that you can reuse the code without duplicating it, and it's compatible among various Python versions, because the PDB modules changed slightly from version 2.5, 2.7 to 2.6, etc. And if we just copied and pasted the code, there was a risk that it stopped working at some point because the interface of the PDB class changed. The disadvantages, of course, is that we introduce some complexity and we have to explain very carefully what's happening. It's a bit fragile because it relies on the load global bytecode, which is an implementation details. It can lead to unexpected bugs. For example, there was at some point I forgot to pass the func defaults to the new function, and so the defaults just didn't work. I didn't recognize until someone complained. But at the end, I think it's still a good solution because I really hate to copy and paste code. So just wanted to solve it. Second problem, open classes. So suppose you have a huge hierarchy of classes, and for each of these classes there are many features which are loosely related, but you would like to keep them separated. This usually happens when you do a lot of implementation of the visitor pattern. you have two ways to access on which to split your functionalities. You can split them by feature or by class. Splitting by class, it's easy. You just write your Python file, you write the class inside, and you put all the methods there. But if you want to split by features, for example, all the methods called foo in one file for all classes, and all the methods called bar on the other file, then you don't have an easy way to do it in in Python. In Ruby, there is the concept of open classes, and you can do exactly this. So what we did, this is a real example from PyPy, and it is in particular the AST compiler, which has this hierarchy of classes, the base class, which is AST, and then a lot of subclasses and subclasses of them, and etc. And in the base class, there are a lot of methods. Now here I present just some, and they are really separated by area and functionalities. There are, I think, yes, the text is a bit too small maybe, but there are the two first methods that you want to put like in asthelpers.py. The second of method you want to put in another file, codegen.py, and the third in another file as well, because it's related to optimizations. So what can we do this? This is another magical thing, and it's really stolen from the PyPy source code. It's a meta class. It's called extendable type. What you do is create your base class. You set this meta class. You write your methods, and it works as expected. You instantiate it. You call the method, and it works. Then what happens if we use this special syntax? We create a subclass of A, but we call it under extend under. We add a method, and then magically this bar method has been attached to the A class. So object.foo still works. Look at the object is an instance of A, and the object.bar works as well. So this is exactly what we need, because then we can just put this extend class in different files, and all the methods goes to the same A class. So what's inside? As I said, it's using the power of meta classes. As I said earlier, in Python everything is an object, and of course every object has a type, or in other words, a class. So a class is an object as well. What is the class of a class? Yes, meta class. So actually what happens when you in Python you write down the class statement, class A, colon, and the body of the class, you are really, without knowing it maybe, you are really instantiating the meta class. So let's look at what happens really. We are at this class statement, we create a class name in foo, which extend bar, and we have some definition in the body. The first thing that happens is that the body of the class is evaluated. It's really just like exec the code. And the result is a dictionary which contains the scope of all the things that happen in the class body. In this case, the dictionary contains my var, which is a number, and foo, which is a function. Then, as I said, executing the class statement is really instantiated in meta class. So we have this meta class, we will see later how to find it, and we pass various parameters to it. The name of the class goes in two places. One is the string containing the name of the class. This is what you see in the rep, or by typing foo.under name under. And it also goes here. This is the variable in the scope where the class statement is executed. And this is why how you can really type foo after having defined the class. Then we pass the list, the tuples containing all the base classes, and then we pass the dictionary containing the result of the execution of the class body. How do we find the meta class then? Well, this is a long story, but to simplify, we simply look if there is this special variable in the class body, which is under meta class. If there is not, we've tried to find the first base class and look at its type. As I said, base class is a class is a type, and the type is a meta class. So we reuse the same meta class as our base, our superclass. If we don't find it, we also try to look in the global under meta class variable. I didn't write it in the slide, but if you don't find any of these, you just use the default one, which, well, in Python you use usually all style classes by default. In Python 3 it's type, the default meta class, and it's also what you get when you inherit from object, because the type of the first base object is type, of course. So once we found it, we call it. So we instantiate our class. Usually meta classes are subclasses of type, because it does most of the work for us. Usually you override the new method, and then you can tweak the parameters and do whatever you want. So what happens? To implement this extend hack, you write your base class, you use this special meta class, which is extendable type, and then look at what happens here in this statement. As I said earlier, this is a normal class, of course, even if there is the underscore, double underscore name. So it tries to find a meta class. We look in the basis, we find A, we see that meta class of A is extendable type, so we are trying to instantiate another one. And in the dictionary, we pass this function called the bar. So if this is a hook that we can use to know when our base class is extended. So look at the logic inside the under new of this meta class. We look if the name is extend, so we are in this case. So, okay. If we are extending the class, what we do, we simply iterate over the base classes, and we set out all the values found in the body of the extended class. We set out on the base class. So this is dict is a dictionary containing bar. So we iterate over it. Key is bar, value is the function. Key is the string bar, value is the function bar. We set out on the class, on the base class, this key and this value. So at the end, we are really doing a dot bar equal to this function here. And of course, there is a special case of what happens if the name is not under extend, which is needed to instantiate the first class in the first time, because when we instantiate the first class here, the meta class is still extendable type, but we don't want to do anything special. So we are in this case, and we simply call new type, and then it's easy. So we can use this hack to solve our original problem. We have this base class AST. We declare this meta class to be extendable type, and then we can simply write our classes exp, statement, and etc. Then in the other files, we can put all the methods called ASNodeList or setContext in AST helpers, and we implement it for all classes, for AST, for exp, for statement. Then in CodeGen we do the same for the other set of methods and optimize the same as well. As usual, there are pros and cons. Well, the pros is the better organization of the code, because you really can split the logic on the feature by the feature instead of by the class, which depending on the case it might be a better idea. It's also well contained magic, because it's really a few lines of code, and you can explain and you can understand it very easily. Well, the disadvantage is that it relies on a naming convention. So if you don't know about this feature, you open the PyPy source code, you find this declaration, definition of the class, and you don't know what to think. But yes, it might be unobvious at first, but if you look a bit in the code, you start to reading it, then you can maybe find it probably easier to understand. Probably the worst bad effect of all is that by doing this we have import time side effects, because as long as we don't import the module, for example, this AST helpers.py, our AST class doesn't have these methods. So this is really an obvious, and it might lead to some unexpected bug, because you don't see this method on the class, and then after a while you see it because somehow this module got imported from some strange path. So what I like to do usually is to really write a comment on the side of the import saying that it has side effects. So you know that you don't have to remove it, even if you're not using any name imported from it. However, this is a cool hack, but sometimes it's even too powerful. From the Zen of Python, you know, simpler is better than complex. So it's a good idea to use as much magic, much magic, yes, as actually needed, and not more, hopefully. So here I have another example of where using this magic is maybe not a good idea, because there is a simpler solution. It's another real-world example that I used. Camelot is a framework for developing database-based application with a nice automatically generated user interface. You use subclasses of entity to define your data model, and you declare the fields and etc. And then you have this admin class, which is a nested class, which you use to declare how the UI looks like the name of this window, or which fields to show, and etc. However, writing the code in this style, as in this example, is not the best of the world, because you are really mixing business logic and presentation logic. So ideally, I would like to split user and admin into different files, one containing only the business logic and the other the admin logic. So one say, yeah, I know, I use extendable type. I use this meta class, I just define the fields here, and in the other file I extend it with my admin class, and everything works fine. However, entity is a special base class which has its own meta class, so you can't just use extendable type. You have a meta class conflict, which means that you have two different meta classes and Python doesn't know which one to use. Anyway, even if we didn't have this meta class conflict, there is a simpler solution, because it's really a slightly different problem than the AST. Here we just have one thing to attach to the class. We don't want to extend with a lot of methods. We just want one admin class to attach it. So we can use this other magic, which is not really magical. We will see the implementation, it's really easy, which I call attach to. So we can just instantiate the class foo, then we use this class decorator, attach to foo, then we define our admin class, and then magically this admin is attached as foo.admin. And then Camelot is happy, we are happy because we split our logic into different files. So to explain how this works, I have to explain a bit about decorators. But actually, when they were introduced, decorators at first didn't look very important feature. It's just a syntactic sugar. In this example, I show like a function decorator, which is called foo, and you can see it because of the 8 symbol before. We decorate this function called myfunc. We also have a class decorator, which is to decorate a class. Well, the same logic. Class decorators are only from Python 2.6 and next. And this file is exactly equivalent to this. You see, decorator is nothing really special. You just call a function, passing a function to it, and you rebind the result to the same name. The same for classes. But since these were introduced, people started to use it in various smart ways, and there is really a whole world of decorator and things you can do with it, just because of the nice syntax that earlier people didn't think about decorating functions or using it. So as I said, attach to is not really magical. It's just like a standard implementation of a decorator. Well, actually, it's a higher order function, of course, because we want to pass a parameter to it. So obj is the object we want to attach the class to. This is the thing that it's actually run as a decorator. Basically, when we do this, we are calling bar, passing 42, and we are using the result as a decorator. Decorator has to be a function. So here we are attached to, we create a function and return it. And the function doesn't do anything special. It just takes the name of the class. In this case, in the example is admin, and set this object, this class, on the original object, which I passed to attach to. It is a closure using the name. So we solved our third problem, because we can just have our class user, which the fields, and then we attach to the user class, the admin class, with the presentation logic. So what are the pros and cons? Well, in this case, simple is better than complex, so it's much better to use this solution than extendable type, especially because the other didn't work anyway. You don't have any meta class. It's much less magic than the others. And honestly, I can't find any disadvantage of using this particular technique. It's just standard Python, you use it and you are happy. And if you don't understand what is attached to function does, you just look at the code and it's obvious. Fourth problem that I had to solve in the past years or months. At some point I was spending a lot of time inside GDB, because you know when you are developing PyPy and the JIT and everything crashes and you have to somehow debug it. And then there is a nice feature in the newer version of GDB that you can extend it with new commands written in Python. So you can, for example, write this new command, which is a subclass of gdb.command. So initialization, here we are defining this mycmd command, and then the invoke method is called whenever we do it at the GDB prompt. So let's try. I can launch Python commands just by typing Python GDB demo. So here I have imported my module, which my command, and now I can use it as a command inside PDB. Hello from Python. Yes, it works. Cool. However, it's a bit annoying to develop, because yes, when the command is ready, you can use it. It's very nice, but when you are developing it, it's really annoying, because if it's a simple command, you can just start GDB as I did and run it. But more complex commands have to rely on some state of GDB. So maybe what you do usually is to start GDB, you start the program, you run up at a particular point, you try your command, you see that it doesn't work because there is a typo, and then it crashes, and then you have to do it again. You start the GDB, you start the program, etc., and then it's really annoying. So what can we do? Well, this is really hack. It's much more magical than the other, and I don't recommend to use it in production code, but it's really useful during development. So I rewrote my invoke command like this. What do? I import the same module. The name of the module here is wrong, sorry, I will correct it. We import the same module as the class is defined. We reload it, so it means that if we change the source code in the meantime, the new class with the new source code is loaded and we can use it. Then we rebind the class self.under class equal to gvdemo2.myCommand. Basically, it seems a no because we are already inside. Well, the class of self is already my command. And then we actually call the actual logic, which is doInvoke, which is hello from Python. And I show you that it works because is it too small, maybe? So this is exactly the code that you saw in the slide. So what do I do? Python import gdb2. I invoke my command, hello from Python. Then I change it, and automatically it's using the new version. What's happening under the hood? So this is another diagram of how various objects are related. This is what happens when GDB calls myCommand.invoke. We have this myCommand object, which is the instance, which has a class, which contains this invoke and doInvoke methods. When we try to look up the invoke methods here to call it, we look up in the dictionary of the object, we don't find it, then we look up in the class, we find it, we call it, and then we start with the code that I showed you. Reload GDB demo, what does it do? Well, it really reloads the module and puts new objects from it in the namespace. So we really create a new class. Note that this class continues to exist. The new class which contains the new source code now. Then I rebind the class, and then this is what the magical thing, because it really seems a no-op, but actually it's really rebinding it to a new object which contains the new source code. And then we actually call doInvoke, which means that now the doInvoke is found in the new class, which I just reloaded. As I said, this is really a hack. It's very useful during development. I use it a lot of times, not only in GDB. It happened in other situations that you have to click, and then really execute the code, and you don't want to do it all the time. Of course, it's very fragile. It makes a lot of confusion because you have two different classes with the same name, so objects are not really compatible, and etc. It might not work in more complex cases if you have variables class variables to pass around, etc. But well, it might be useful during your development. So I think we are running out of time, because how much time is left?
7 minutes.
7 minutes. I tried this bonus spell to go back in time and have some more time, but I suppose it doesn't work, because how much time is left now? 7 minutes. Didn't work, sorry. So I suppose I just jumped to the conclusion, because I had one more magic to show you, but I already knew that I didn't have enough time to show.
Oh, there's 7 minutes.
Yes, no. That's why I wanted to jump to the conclusion and.
You have 10 minutes after this.
Yes, I know.
Okay.
I know. I wanted some more. There is no time to explain this last magic hack. So I'm just with 5 minutes more question if you have. So what is the conclusion of this talk? Well, there are these magical features, they might be helpful because I don't know if I managed to convince you that it's a good idea to use them, but from my point of view, somehow it really helps to reuse existing code, to improve the readability, to improve the testability. Well, this was the last magic that I didn't show. Of course you have to use with care, because you should do it only if you really know very well what you are doing. And I hope to have explained to you how it really works under the hood for the things I showed. And if you really are going to use this, please write a lot of comments in your code explaining what's going on, because if I happen to read it, I would like to understand, please. Well, the other obligatory citation about this topic is that the famous quote from Brian Kernighan: debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are, by definition, not smart enough to debug it. So, actually, if you are used with care. So I think I'm finished. Here are some contacts. You can find the slides and the code on this repo on Bitbucket. You can find me on Twitter. As I said, I'm available for consultancy and training, and if you have any question, I'm happy to answer. Thank you.
I saw some code where the meta class was a function and not the class. What is the advantage?
Actually, I think that in this particular case, there is no advantage because, well, it depends what the function returns. Actually, as I said in this slide, I know where to find it. Yes. Well, instantiating a class is really calling the meta class. So from a point of view of Python, it can be any callable. You can really have a function which returns 42, and after this instantiation, the name foo contains 42. If you have a function which returns a normal class, yes, you can do it, but then you lose probably the main advantage of meta classes, which is that they are automatically reused in subclasses, as in the extend hack I showed. Because if you don't need this automatic meta class in the subclasses, probably it's much easier and simpler to just use a class decorator. You have your class, your code is automatically the class object is passed to the decorator, and you can add methods and attributes and do whatever you want. So I usually don't think it's a good idea to have a function.
So two things. One about reloading. Guido actually tried writing a reload function for modules that really almost works. And it's a little more clever than yours because what he does is he actually copies the attributes into the old class object. So it works a little bit better probably than what yours does. My question actually is about the second approach to extending a class. I tried it on my laptop while you were talking. I was quite surprised to find that functions worked because there is a concept in Python 2 of an unbound method object, and a function that's defined inside of a class, if you refer to it without an instance, it is an unbound method object and you can't call them. And I was quite surprised that functions worked there.
You mean where is it? You mean this one?
Yes, attached to, yes. So you're inserting an admin, which is a class object, but and I guess it's a callable, but that it's not being called through the instance. It's not a method. And if you do that with a function, it works. And I was quite surprised because they are not unbound method objects.
Because unbound methods are created at lookup time. So in the dictionary
lookup
of the class,
through self, yes. But my question is there some difference between an unbound method object and a function that is going to bite you with this approach?
No, but I mean, you can use attach to even for functions, probably.
You can.
Yes, but because really if you are calling attach to on a function, then it really puts the function on the dictionary of the class. And this is what happens normally, because
Yes.
if you have...
Yes. My point was that they're actually slightly different because it's the unbound method, which we got rid of in Python 3 anyway, so it works completely in Python 3. But
So I think I didn't understand the question, because, like, you see, in the dict there is a function. It's not an unbound method. It becomes an unbound method only when I... okay. I suppose I answered your...
Okay. Another question here.
How much of this white magic works on PyPy?
all of it, I think, yes. Yes, because the only thing which relies on implementation detail is maybe load global. I mean, defining the function, but actually I think that having the func global attribute, I don't know if it's in the language specification, but it surely works on all on Python and CPython and PyPy. I would suppose that it works also on EuroPython and Jython. So. Yes.
So I'm still not sure of when I would use a meta class versus having a class decorator. It seems like your example of the extendable could also be implemented with the class decorator.
Yes.
So when is the trade-off? It looks like whenever anything is creational, I can use the class decorator just like I could use a meta class. There's only other things I would want a meta class.
Well, actually, in PyPy, it's like this because it was developed before class decorator were introduced. So this is the very easy answer. And then, yes, it's really some. We can discuss all the time if one solution is preferable to the other. Actually, I think that extended is really nice because you don't have to import the attached to name all the time, for example. So if you have a lot of modules that you want to split your logic in. Yeah.
But then it's hidden magic.
Yes, I know, but once you get used to it, well, I mean, after a while it's really obvious what's going on. But yes, I agree that it's at first it might not be the best thing to do. I don't know. After a while I'm used to it. It's really obvious.
So I've got a question. How do you resolve name collisions both in extend and attach to? Meaning that I might create my own extend class that overrides your other method that was added by an extend class, and same thing with the attach to.
Well, no, that is really equivalent. Basically, we don't do it. You look at the code and you don't. And it's really equivalent to write the same method twice in the class. Like if you do this.
Yeah, exactly. I mean, it's exactly the same thing with one big difference. That if def bar is twice in the same file, I see it.
Right.
And that's a big difference.
Yes, I agree. Well, it's very easy to extend this, the meta class to detect this case and complain. Yes. I think it's probably a good idea. We should do it in PyPy as well. Thank you. Patches are welcome. Right, attached to should have the same logic as well, yes.
So what's the last magic hack?
Yes, well, the story is the one which takes more time to explain, so that's why I just didn't even try. Basically, if you use Elixir, which is the predecessor of SQL Alchemy, the declarative, you have a global implicit dictionary, metadata, SQL Alchemy metadata, so a global database, and all your classes belongs to this database. But this is very hard to test because if you really try to test your business model, then you are going to use the database, to use when you run normally the code. Yes, you could monkey patch metadata, but you have to make sure to monkey patch it before the model is imported, etc. So what I did was to fake the importing logic of Python. Basically, I have this file, and I really import it more than once, and every time with different globals. And here I'm really doing what Python does to import a module. So I create a new module. I set the file name. I update sys.module. Here is some magic thing, because in these particular lines I set the fake global data, which are really local, because I use different values for each database I want to instantiate. And then I compile and execute the code. And then, of course, well, I remove it from sys.module because it's not really a module, but well, Python doesn't do usually, of course. And it's another hack, and this is to work around the limitation of my library, well, not mine, of Elixir, because it doesn't let you easily to have local state instead of global state. So at the end, I can just instantiate my database, passing the path to the model file, and I can have more than once in tests, so every test run in its own database in isolation and etc. Well, I don't expect you to have understood everything of what I said, because I compressed in 2 minutes something that should have taken 10.
Just a remark, the previous slide could just be copied as an answer to the question, why is there no Python compiler?
Why there is no?
Guido stated in his speech that he often gets asked, why is there no real Python compiler? And your previous slide may be just the default answer to that question.
Yes. Yes.
Hi, when we're defining meta-classes, we're told to always use under new and not under init. And as far as I'm concerned, that's like just a recipe for doing it. But I wonder if you could shed some light on why it's done like that.
So the question is why I use under new instead of under init. I think that this particular case doesn't change much. Well, I don't remember with the slide, but in general, if you want to change a thing like the name of the class or the basis, you should do it in new, because then it's too late. There are attributes which are immutable, and new is the function which creates the object, and init is just something that modifies it after the creation. And well, also it is standard practice to override new for meta classes, so just do it and be happy.
Are there other questions? Yeah, this is the last one.
Hello. Are there any changes that you think from all of this that you could simplify Python to make all of this not necessary?
Should ask this to Guido. Well, I don't know about simplifying, because it's not that I had to do this because Python is complicated. I had to do this because problems are complicated. And yes, if Python supported open classes as Ruby, then you don't need the extend ACK. But then it's not simplifying, it's making it more complex. So yes, you could add features, and don't know if it's a good idea to have them in the core language or not.
Okay, yeah, time's up. So thank you, Antonio.